Kia ora tātou. Welcome to this video where we will look at concentration and how that affects the rate of a reaction. So let's picture what concentration means if we're talking about a particular reaction. So let's say we've got a solution of acid. So let's say this is HCl. The important particle within HCl that will react with a base that we put into the solution is the hydrogen ions. So we've got a few H plus there, 3, let's say we've got 4 in this one, and let's say we've got, 6 hydrogen ions in this solution. And they're the same volume. So if they're the same volume, if they're both 10 mil, then that means that this one's got 4 hydrogen ions per 10 mil, and this one's got 6 hydrogen ions per 10 mil. So this one is a lower concentration, and this one is a higher concentration. So if in each of these solutions we were to put, let's say, some sodium hydrogen carbonate, HCO3, which is a powder, let's say we put 1 gram into each of these solutions. This one would have less collisions per second because there are less hydrogen ions moving around in the solution, whereas this one would have a greater frequency of collisions because there are more hydrogen particles. This one here, because there's more hydrogen particles moving around in that solution. So that's basically it, and then it's learning how to write an exam answer. So this is the same question that we went over for surface area. So cleaned magnesium ribbon reacts with hydrochloric acid. So we get magnesium plus hydrochloric acid goes into magnesium chloride and hydrogen, other products. The reaction is monitored by measuring the volume of hydrogen gas produced over a given period of time. This is shown in the graph below. Explain the changes in the rate of reaction between magnesium and hydrochloric acid in terms of collision theory. Refer to parts A, B, and C of the graph in your answer. So part A, we've got a very steep slope, so that's steep. Then part B, it's less steep, and then part A is horizontal, let's say flat. And we need to refer to the information that we've been given in this graph when we're giving our answer. So let's draw 3 beakers to show part A, part B, and part C. So I'll just do, so we've got the magnesium ribbon that we're putting into here. Let's just show hydrogen ions are these black circles, and then the products, so magnesium chloride and hydrogen gas. Well, the hydrogen gas will be escaping, so I can draw them up there, will be shown by red circles. So in the first instance, we've got all reactants. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 reactants. In the next section, we might have 1, 2, 3, 4, 5, 6 reactants, but then we've got some magnesium chloride and we've got some hydrogen gas that's been released. So the number of particles of reactants that we now have in the solution is less. And then finally in part C, we've got some magnesium chloride in here and we've got some hydrogen gas that's escaped. But we've got no more reactants left. So we need to explain what's happening in terms of concentration at each part of this, at each part of the graph that was in the question there. So in part A, we would say that there is a high concentration of reactants. Therefore, there is a large or a higher frequency of effective collisions. This means that there is a high rate of reactions, and this is shown by this, like the steepest part of the graph. pH. So we're relating back to the evidence that we can see in the graph itself. Then part B equals sum of the reactants have turned into hydrogen gas and magnesium chloride. So there are less reactants, and we would say there's a lower concentration of reactants as well. So there are going to be less, a lower frequency of effective collisions. So always just relating back to effective collisions. And so there will be a lower rate of reaction. And this is shown by the graph in that it's less steep. And then finally in section C, all of the products, I'm just going to go like that, all of the reactants have been used up. So no more collisions. And this is shown by the flat part of the graph. So that's shown that there's no longer any products being produced. So let's have a look at what the model answer says. So initially the rate of reaction is fast, as shown by the steepness of part A in the graph. This is because the concentrations of the reactants are at their highest, resulting in a high frequency of effective collisions. So the rate of reaction is highest there. As the time proceeds, there are products being formed, so the concentration of reactants decreases, resulting in fewer particles available to react. This results in a decrease in frequency of effective collisions between reacting particles and a decrease in the production of hydrogen gas, as shown in part B of the graph, where the gradient of the graph becomes less steep. Consequently, the rate of reaction decreases. So it is quite arduous to get to the level of a model answer, but good challenge if you can make it. And then once all of one reactant or both has been used up, the reaction will stop. So no hydrogen gas is produced, as shown on the graph in part C as a horizontal line. So that's concentration. This doesn't actually come up very often in an exam, and when it does, it comes up like this. You won't get a comparison between one solution is like 0.1 mole per litre and another solution is 0.2. Concentration is normally comparing different periods of one reaction. So in the next video we will look at temperature. Thanks very much. See you then.